So we're going to work through this one. Remember, it just says graph f of x equals x to the third, blah, 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 using what you've learned in this section. So we're going to start with our our end behavior. Highest exponent is odd, and it's positive, which means this falls left, rises right. And then I want to look for my roots. This is not factorable, so I have to do the possibles. This is just 1. This would be 1 and 7. So it's plus and minus 1 over 1 and plus and minus 7 over 1. Makes life a little bit easier because there's only 4 to test. Then we test them. So I'd get 1, 6, 12, and 7. Put the 1 on the outside. 1, 1, 7, 7, 19. Not going to work. Negative 1 goes on the outside. 1, 6, 12, 7. 1, negative 1, 5, negative 5. 7, negative 7, and there's the one that works, which is negative 1. So one of my zeros is negative 1 with a multiplicity of 1 for now. Then I look at my quotient here, ignoring the remainder, which is x squared plus 5x plus 7. This is not factorable, so a is 1, b is 5, and c is 7. Negative 5 plus and minus the square root of 5 squared minus 4 times a times c all over 2 times a. Negative 5 plus and minus the square root of 25 minus 28 over 2. So now I've got an imaginary root. Negative 5 plus and minus the square root of negative 4 over 2 means it's 2i over negative 5 plus or minus 2i over 2. So those are roots, but they are not real roots. They are not going to show up on my graph. So the only real root I have is negative 1.
So on the test, we just put negative 1.
Yeah, you'll probably get 2 other real roots on the test. Like where you have to do the quadratic like that. Yep.
So if there wasn't, let's say there was an answer that wasn't a real root for the zero, would you put that?
So if it says list all zeros, you include it. If it says list all the real zeros, you don't include it. Then I want my y-intercept. So remember, if I plug 0 and 0 and 0 in here, I just get 7. So y-intercept is 0, 7, which is all the way up here. My arrow points down and up. So my graph is pretty consistent with a normal cubic function. It can't be a straight line.
Wait, sorry, what did you plug into the equation to get 7?
0. So to get the y-intercept, you plug 0 into x. And then I'm going to go to the graphing utility so we can see what this looks like on that.
So when it says fall left and runs right, like anything on the left side of the graph has to be pointing down?
Correct.
Okay.
Yep. The last 0 to the left has to have an arrow pointing down. The last 0 to the right, which in this case is the same, has to have an arrow going up. Yep.
Plug in points and stuff.
Or use the intercepts. Like there might be enough. You might have to plug in like maybe 1 point, not a bunch. Questions on this example? So again, feel free to use your graphing utility to help you like verify things, but remember you won't have it for your test, so don't rely upon it.
So on the homework, I got like one of the questions, like one of the numbers I had to plug in, it got like -3, like -216.
Just plot it and label it.
Are they gonna be like that big on the test?
I don't think that big. They could be bigger than your graph though, and those you just plot and label. They don't, yeah, no, I'm not gonna, like even if you had -20 and it's off your graph, you don't have to go all the way. Just plot it and label it. Yeah, as long as you label where it's going, you're fine. Okay, so I'm gonna come back, like I said, I'll work these out, but. All right, I'm gonna work through the homework examples. So for 35, I'm actually gonna start with the end behavior. The x is squared and positive, so they both point out. To get the zeros, I can actually factor this. This would be t minus 3 and t minus 3. Set them each equal to 0, and t equals 3 and 3. So the zeros are just 3 with a multiplicity of 2. The y-intercept, I would plug 0 in here, and I'd get 9. So when I go to graph it, I'm going to plot my positive 3 and my 9. Both arrows point up, so it goes up to the right and up to the left, which is our standard parabola. And then you can just use the graphing utility to verify. 38, my end behavior again is both up because it's squared and positive. I'm going to do 0 equals 1/2 x squared plus 5/2 x minus 3/2 and actually multiply by 2 to get rid of the fractions. And I get x squared plus 5x minus 3. Not factorable, so I have to use the quadratic equation. -5 plus and minus the square root of 5 squared minus 4ac all over 2 times a. -5 plus and minus 25. -4 and -3 is plus 12 over 2. -5 plus and minus the square root of 37 over 2. So when I list my zeros, it's -5 plus root 37 over 2 and -5 minus root 37 over 2. Both of those have a multiplicity of 1. When I go to graph them, however, I have to approximate that root 37. So let's say this is like 6.2. -5 plus 6.2 would be 1.2, divided by 2 and I get 0.6. -5 and -6 and -11.2 divided by 2 and I get -5.6. The last thing is the y-intercept, plug zeros in here and I get just -3/2. So my first 0 is 0.6, the other one is -5.6, and my y-intercept is -3 over 2, which is 1.5. This is obviously a parabola, so I can put my arrows up on both sides. I know it's going to cross through, so it's going to come down. It has to cross through, it comes down. And I want to know how far down it goes. So you can either, you kind of have two choices here, plot a point in between there and just see how far it goes, or because I know it's a parabola, I can find my vertex. So to do that, I can do -b over 2 times a. -5/2 over 1 is -5/2. So -2.5 is the x coordinate, and then plug that back in. So 1/2 -5/2 squared plus 5/2 -5/2 minus 3/2. 1/2 25/4 minus 25/4 minus 3 over 2. I get 25/8. Change this so it has that denominator, minus 50/8. Change this so it has that denominator, minus 12/8. -25 minus 12 is -37/8. So -3/2, -37/8, or -2.5 and -4 5/8. So now I know how low to make it. At -2.5, I go -4 5/8, and then connect your parabola. 40, I'm going to work out over here. Okay, so end behavior, I'd actually have to multiply this to get t, it'd be 3t to the 4th, and that's an even, and this is positive, so they're both up again. To get the 0, this is 1, t squared would equal 0. T would actually equal plus and minus square root 0, which means there's a positive and a negative 0, which the signs don't matter. What it does matter is the multiplicity on that is actually 2. Now the second one, multiply 3 times 7, and you get 21. Factors of 21 that sum to -10 would be -3, -7. 3t minus 3t squared, sorry, minus 3t minus 7t plus 7, group it. Take out a 3t, t minus 1, take out a negative 7, t minus 1, t minus 1, minus 3t minus 7, and I get 1 and 7/3. So now my zeros are 0 with a multiplicity of 2, 1 and 7/3. My y-intercept, if I plug 0 in, 0, 0, I'd end up with 0 squared times 7, which is 0. So the y-intercept, so go to 40. Y-intercept is 0, 0. That's also one of your zeros. The x is 1, and the last root is 7/3, which is 2. 7/3 would be 2 and 1/3. Both arrows are pointing up. It's gonna bounce off the 0, come back through the 1, go down and come back up. If you want to see how low it goes at the 2, you can just plug in your point. So 2 squared, 2 squared, minus 10 times 2 plus 7. I get 4. 3 times 4 minus 20 plus 7. 12 minus 20 plus 7. Negative 8 plus 7, which is negative 1. So 2, negative 4. And that's what my graph looks like. All right, 41. I'm gonna work down here. So highest exponent is now odd. Positive means this falls left, rises right. To get the zeros, I can take out a 3x. There's no factors of 1 that sum to 4x. So this set's equal to 0, and x is 0 from there. But the second one, you have to do the quadratic. Negative b plus and minus the square root of b squared minus 4 times a times c all over 2 times a. This is 4 and 3. 2 plus and minus the square root of 3. So I have 0, 2 minus square root 3, and 2 plus square root 3. Square root 3 is like 1.7. So 2 minus 1.7 is 0.3. And 2 plus 1.7, 3.7. Last would be the y-intercept. Plug zeros in, and I get 0, which is consistent with that point. So 0.3, 3.7, falls left, rises right. Multiplicity is all 1, so it's going to cross through. I don't know how low here, so I'm going to plug in a 2. So I'm just going to mark it because that's really low and it's off my graph down here. And I'm going to say 2, negative 18. So this is going to come all the way down here, come back up and cross through at that 3.7. Okay, last one is 42. So it's a even exponent positive, which means both are up. I can take out an x squared this time. Factors of negative 30 that sum to positive 1, negative 6, and positive 5. This is 0, and again, plus or minus 0, so it's 0 with a multiplicity of 2. This is 6 and negative 5. Y-intercept, 0, 0, 0, would be 0, 0. Negative 5, 0, positive 6, both up, crosses through, comes back up, bounces, crosses through, comes back up. So I need to know how low to put. I'm going to plot 3, and then I'm going to plot 3 over here. So -3. I get 81 minus -27 minus 30 times 9. So that's really low. I'm going to just plot it. So -3, -162, obviously way down. And then I also want to do the same thing with +3. And again, I'm just going to plot it 3, -216. So it comes down, goes back up, bounces at the 0, comes back down a little bit lower, comes back up, and crosses through that last point. Here's the last two, which were the graphing utility. This is 3x to the third minus 13x squared minus 17x plus 7. And this is 5x to the third plus 4x squared plus 14x minus 3. I want to work through 4-1. So 4-1 is, without rushing through that part, okay? 4-1 is called rational functions and asymptotes. So it's continuing with the graphing, although we don't get to much graphing today. In 4-2, we start to graph these a little bit more. So you're going to continue to see things like zeros, which is good. That's good practice. You might see something where the multiplicity is 2, so it bounces. Like all that stuff is good because it's repetitive practice. But what's different is the types of graphs you're going to be graphing in this section. So this is what a rational function looks like. If I were to graph 1 over x, which it's been a little while since we did the parent function on that, but we did talk about it. It goes, oh no we didn't, not here, no. It goes up to the right and down to the left. So it has what are called asymptotes. Okay, and asymptotes occur where your graph would be undefined, and it's based on your domain. So if you remember domain restrictions, we said that a function's domain would have been all real numbers. Audrey, you with us? I only say that because I know you're not. Okay. All real numbers except when there was a variable in the denominator, when there was a variable underneath the square root, or the combination of those two. Remember these? We restricted our domain based on those occurrences. So you're not going to see square roots in this section, but what you will see almost every single time is actually that's a lie. You will see it every single time, is a variable in the denominator. Whatever value makes that 0 is undefined, which results in an asymptote. So you can't see it really from this graph, but there is a dashed line here that's called your vertical asymptote. It's a vertical line, thus the vertical part. And then it's an asymptote which says the value that is on that line, which is x equals 0, cannot be plugged into this function. If I plug 0 in there, I get 1 divided by 0, and that is undefined. This is a whole lot of like notation for basically saying as x approaches, so the little arrow means approaches. As x approaches 0, the positive means from the right. So as I move towards 0 from the right, my function reaches positive infinity, so it gets higher. As I move from 0 towards 0 from the left, which is this part, my function approaches negative infinity. You'll never be tested on function notation. Just know that that's there. If you're like start to look in your book or an explanation of rational functions, you'll see that stuff. There's also on this graph a horizontal asymptote, which is a line that is horizontal, that provides a guide for those curves. In just a moment, I'm going to teach you how you find those two. So there's vertical asymptotes, there's horizontal asymptotes, and there's something called a slant asymptote, which we'll talk about too. So the vertical asymptote, to find it, we set our denominator equal to 0. So whatever's in the bottom, we set it equal to 0 and we solve. There could be one of them. There could be more than one of them. Sometimes we have to factor to solve it, okay? And those lines, the graph cannot cross. You can't draw a line, your curve through those lines. Those lines are a brick wall. It can't go through it, okay? The horizontal asymptote, it can cross. So it's weird, but it can cross it. Sometimes you end up with a graph that has two vertical asymptotes and a horizontal asymptote, and the outer two look like this, and the inner function actually crosses through the horizontal asymptote, okay? It cannot cross through the vertical, but it can cross through the horizontal. What the horizontal really does is affect the arrows on the outside. So it says here, get close to without touching this line, get close to without touching that line on the outside. But that inside curve can cross through. Okay, it doesn't always happen, but it can. Yep.
The horizontal one is it always going to be on the line of the graphic?
No, so that's what this whole thing is here. The way you find the horizontal asymptote. Okay, so if you're like sleepy, smack yourself, because this is super easy if you understand it. And then if you don't listen to me for the next 4 minutes and you try to figure this out on your own, I wish you lots of luck. All right? So there is 3 cases with horizontal asymptotes, and they are all based on the highest exponent in the numerator and the highest exponent in the denominator. So if I have x squared over x, let's just say that's my function. Okay, obviously there will be more to that, but let's just look at it for there. The highest exponent in the numerator is 2. The n is what we use for that, n for numerator. The highest exponent in the denominator would be 1. The m we use for denominator. And then you want to compare those. They're either going to be this, where n is less than m. It's going to be this, where n is greater than m. Or it's going to be this, where n is equal to m. If n is less than m, then the horizontal asymptote is the x-axis, y equals 0. If the n is greater than m, then there's no horizontal asymptote. If the n is equal to m, then there's an asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So leading coefficient is the number in front of the exponent that has the highest exponent. These will all be horizontal lines though, because if you think about it, if it's a number over a number, it still doesn't have an x, right? That's still a horizontal line. And then this third special case is if n is 1 more than m, there's a slant asymptote.
So like in the case that you just showed us, it would be a slant.
Correct. So this one actually has a slant asymptote. If it was reversed, if I had x over x squared, now the n is 1, the m is 2, the n is less than m, so it would be 0. If I had 2x to the third over x to the third, now they're the same. So the leading coefficient in the top is 2. The leading coefficient in the bottom is 1. So it happens at y equals 2. Yep.
What if there's like more than one term?
You always look at the highest one. You're going to see. We're going to do a bunch of examples on this.
When
Yeah.
you say it happens at y equals 2, do you mean like
It's actually a horizontal line where y is 2. So you go to where y is 2 and you draw your horizontal line. Yep. Okay, and then there's super fun, extra special cases called holes. And I say that very sarcastically. Okay? Called holes. And a hole exists if you can simplify the function by crossing through a factor in the denominator. So if I am able to like factor what's in my expression and I can cancel out a factor, I no longer have an asymptote at that because it's gone, but I have a hole in my graph. And we'll see examples of that, okay? When you write the hole, it's given as a coordinate point. So it's given as an x, y coordinate point. Sheet for this test, I'm sure as heck going to include, maybe shorthand that, but you definitely want to include this slide, okay? So if I'm going to like have a reference. All right, so let's find just the horizontal asymptote, okay? So just horizontal, I'm making up words today. Horizontal is all I'm worried about, okay? So I want to look at my function. Number 1 says 3 over x minus 1. What's the highest exponent in the numerator? 0. There is none, right? So the n is 0. What's the highest exponent in the denominator? 1. So the m is 1. What's the relationship there? So n is less than m. Good, right? Go back to your little note you just wrote down. And what happens when n is less than m? It's y equals 0. So eventually we're going to put that on a graph. For right now, we're just identifying it. Go to 2. What's the highest exponent in my numerator? 1. What's the highest exponent in my denominator? 1. M. What's true about these? They are equal. What happens when they're equal? Leading coefficient of the numerator over the leading coefficient of the denominator. So what's the leading coefficient in the numerator? 2. What's the leading coefficient in the denominator? 3. So y equals 2/3.
And so we don't look at the two numbers.
Not when you're finding the horizontal asymptote. Nope. Those would affect my vertical because the bottom's going to set equal to 0. And it would affect my 0 because the 0s you set your numerator.
The leading coefficient is always the one with the highest exponent?
Correct. All right, 3. Highest exponent in the numerator. 2. Ooh. Highest exponent in the denominator. 1. Relationship here? N is greater than m. Good. Which means what? It actually means 2 things. It means there's no horizontal asymptote. And because it is one more, it only can be one more for it to be a slant. There is a slant. Which again, we're not gonna, we just know it's there. We're not there yet. If it was 3 and 1, let's say, then there's no horizontal and there's no slant. For a slant, it can only be one more.
What's it about like slant like that?
It's actually like a line. So you can have a graph that looks like this, and then your curves look like that. They make like an X. Yeah. But don't freak out about that yet. We're not there. Questions on those before we go on? All right, now it says vertical and horizontal asymptotes. So the vertical, I set my denominator equal to 0. So I'm going to set this equal to 0 and solve it. 3x squared equals -1. Divide by 3. X squared equals -1/3. Square root. Putting a plus and minus at the front. And I get x equals plus and minus the square root of -1/3. Are those real numbers? No. So there's actually no vertical asymptote. If there was a number there that I could solve for, then x equals whatever that is my vertical asymptote, which you're going to see in about 30 seconds.
Do anything with the top?
Yep. Yep, now we got to use, for the vertical asymptote? No, vertical asymptote is just the denominator. Because you can have a 0 in the top, right? That's an okay answer, it's 0. But if you put a 0 on the bottom, it makes it undefined, and undefined means there's an asymptote.
But if you got the bottom one, then would you continue?
If you got the bottom one, there'd be an answer there. So let's just say that's at x plus 1. My equation would be x cannot equal negative 1. I mean, x equals negative 1. And that would be your equation. Yeah, which you're going to, we'll get to in a minute. All right, how about horizontal asymptotes? What's the exponent in the top? Highest exponent in the top? 1. Highest exponent in the bottom? 2. What's the relationship there? N is less than m, which means? Good. Oh, I'm sorry. That's what you meant by keep going? Yeah.
So the vertical asymptote, you have to solve for the denominator, and the horizontal, you use the exponents.
Yep. All right, 2. Start with the vertical. So set my denominator equal to 0. There's 2 ways to do this, right? What's one way to solve x squared minus 1 equals 0? I can factor it, x plus 1 and x minus 1, because that's the difference of 2 squares. Set them, that should be a 1. Set them each equal to 0, and I get x equals negative 1 and x equals positive 1. What else could I have done? Good. The even root property, right? So set it equal to 0, move it, square root it, and this is why it's so important to remember the plus and minus. I hear you. So that's horizontal, that's the vertical asymptote. X equals negative 1 and x equals positive 1. There's 2 vertical asymptotes. There can be multiple vertical asymptotes. There can't be more than 1 horizontal. All right, now horizontal asymptotes. So what's the relationship between the numerator and the denominator this time, the exponents? They're the same. So this is my leading coefficient part. Leading coefficient in the top. 2. Leading coefficient in the bottom. 2. What's on the front? 1, yeah. So y equals 2. Okay, now we're going to work out number 3, and this time I'm going to do it in the order of checking for the holes first. So I know in class we did it the other way. I want to do it checking the holes first so you learn to start doing it that way. So I have to factor both the top and the bottom this time. I get x plus 2 and x minus 1, x minus 3, and x plus 2. So because these cancel, there's a hole where that equals 0, which means x is negative 2. Then from here on out, we're only using x minus 1 over x minus 3 as our function. So the vertical asymptote comes from the denominator. X minus 3 equals 0 means x equals 3. The horizontal asymptote, highest exponent in the top 1 and in the bottom 1. So it'd be y equals 1 over 1, which is 1. So I lost one of the vertical asymptotes, which is why it's more beneficial to cancel at the beginning and then work it out. To find the hole, I have to take this negative 2 value and plug it into my simplified expression. So negative 2 minus 1 over negative 2 minus 3, negative 3 over negative 5, which is 3/5. And that's the coordinate of my hole. So when I go to graph this, just so you can get an idea, I'll have a vertical asymptote at 3, a horizontal asymptote at 1, and then there's going to be a hole at negative 2 and 3/5. So my graph is going to come through here, but there's going to be a hole in it, and then continue, and then the graph would also go there. Now looking at 4, we're going to factor this. So 3 times negative 6 is negative 18. Factors of negative 18 that sum to 7 are positive 9, negative 2. 3x squared plus 9x minus 2x minus 6 gets factored. 3x, x plus 3, negative 2, x plus 3, x plus 3, and 3x minus 2. In the denominator, I factor x plus 1 and x plus 3. So the x plus 3's cancel, which means there's a hole at -3. Again, you set it equal to 0 and find the hole. Now I'm working with 3x minus 2 over x plus 1 because that's what's left. Set my denominator equal to 0 to find the vertical asymptote, which is at x equals -1. Horizontal asymptote, exponent in the top is 1 and in the bottom is also 1. So this is the leading coefficient, 3 over 1, which is 3. To find the rest of the whole, I'm going to plug that in here. 3 times -3 minus 2, -3 plus 1, -9 minus 2 over -2, -11 over -2, which is 11 over 2. Okay, so now that we go through all of this, it says vertical and horizontal asymptotes. And now that we know that there could be holes, before I find anything, I'm going to see if I can factor and cancel out. So when I look at number 5, nothing can be factored, which means I can go straight to the vertical asymptote, set the denominator equal to 0, 2x would equal -3, and x would equal -3/2. Horizontal asymptote, exponent in the top is 1, exponent in the bottom is 1. Those are both the same, so it's the leading coefficient. Y equals, now the leading coefficient on this is -7 and this is +2, so it'd be -7/2. So when I go to pick this out against a graph, keep in mind that I'd have a vertical asymptote at 1.5 and a horizontal asymptote at -3.5. Number 6, the top can't be factored, the bottom, x plus 3, x minus 3. Algebra 2, crossing, and I get, so now I know there's a hole. And the hole is where this equals 0, which is at 3. Then I'm going to plug it back in to get the remaining. This becomes 1 over x plus 3 when it's simplified. So to find the vertical asymptotes, there's still 1 at -3. Horizontal asymptote, the exponent in the top is now 0, and the exponent in the bottom is 1. So there's a horizontal asymptote at y equals 0. Now to find the hole, I'm going to plug it back in. So I'm going to plug it back in here after I simplified. 1 over 3 plus 3 is 1/6. So it happens at 3 and 1/6. You have to plug it in after, otherwise it's always going to cancel out and give you the 0. So you got to plug it back in after you've simplified it to get the hole. Vertical asymptote, horizontal asymptote, and hole. 7, I factor x plus 2, x minus 2. Denominator, x minus 2, x minus 1. Factors that cancel are x minus 2, which means there's a hole at x equals 2. And then I'll plug it back in. Now I'm working with x plus 2 over x minus 1. So if I plug it back in, I get 2 plus 2 over 2 minus 1, which is 4 over 1, and it's 4. Then I want to find my vertical asymptotes. There's still a denominator, so it's at x equals 1. Horizontal asymptote, the exponents are both 1, so leading coefficient is 1 over 1, which is 1. And 8, factor, positive 2, negative 1. 2 times 2 is 4. Factors of 4 that sum to 5, 1 and 4. Factor by grouping it. Take out an x, 2x plus 1, take out a 2, 2x plus 1, and I get 2x plus 1 and x plus 2. The x plus 2's can cancel, so there's a hole at negative 2, and now I'm using x minus 1 over 2x plus 1. To find that hole, I would do negative 2 minus 1 over 2 times negative 2 plus 1, negative 3 over negative 4 plus 1, negative 3 over negative 3, which is 1. Vertical asymptote, set my 0 in the bottom. 2x would equal negative 1, and x would equal negative 1/2. And horizontal asymptote, again, exponents are both 1. Leading coefficient in the top is 1, bottom is 2. So my horizontal asymptote is at 1/2.